Hey, you guys, welcome, welcome. We're in section 11.4. Are you ready for this? Are you sure? Okay, this is what we're covering. We're talking about the limit comparison test and the comparison test. This is a game where you want to know the convergence, divergence of a series, whatever it might be. Does it converge? Does it diverge? Inquiring minds want to know. And what we do is we compare it to another series that we do know about. Say it looks a lot like a series that we know about, then we would run one of these two tests in order to show whether it converges or diverges. There are two tests here, so there's going to be two quick videos on this technique as well. Okay, the first one is going to be dealing with the comparison test. I mean, in other books, the basic or general comparison test. You're just taking a look at a guy and going, does it converge or not, by comparing it to another one. But next video is about the limit comparison test, which by far you're going to want to use, at least the way I do it when I'm doing the homework. To me, it's the fastest way to get the job done. But there are problems where you just can't do it without the basic comparison test. So what is this first test all about? Well, this is how I kind of explain it. It's good for, we're going to do these two types of problems. I've got a series floating around. I don't know about them. Okay, so a series A sub n. Okay, but what if I knew that A sub n was always less than or equal to the terms in B sub n? What I'm really should say, well, I'll just leave it like that. I'll say this: A sub n is less than or equal to B sub n, and B sub n is, therefore the series B sub n is larger than the series A sub n. Now these guys, an and bn, are all the terms are greater than or equal to 0. They have to be positive term series, otherwise this won't work. So you notice how we're kind of locked into positive term series right now? There is a section later with negative. We'll talk about that when we get there. So if the terms are less than or equal to the terms of another series, now here's the thing, and the bigger series converges, let's say you know that, then what that does is it forces the smaller series. It implies that this guy also converges. Now, people go, what the heck are you talking about? Well, here's the thing. Maybe we have a number line to explain it. If we were to look at the sequence of partial sums, okay, if I were to look at S1 is A1, and over here T1 is B1 or something, S2 is A1 plus A2, and T2, you know what I mean, is B1 plus B2. What we would see is if we plot these guys, every time I plotted A, let's say I put A in red, and this is the sequence of partial sums. You keep adding numbers, but the B guys' terms are all bigger, whatever they might be. Here's the thing. If the top guy is converging to some sort of number L, okay, so I'm talking about these B, in fact, let's change the scale. Let's make it a lot smaller. These partial sums are approaching L. Then what does that say about the smaller series? Can he go beyond L? L, no. It's a joke. No, he cannot go past L because all the terms in A are smaller than the terms in B. And if the B terms converge to some number, you got that red A term we're thinking about trapped. It's increasing, monotonically increasing, and bounded above, and it forces your series to converge. So think of it as, here's one guy, and I don't know what he's doing, but he's bounded above by another guy. He can't do anything but converge. And the other way too, by the way, we can also, if we think it diverges, we can do this little game, C sub n, let's say, okay? So I should put it up here. C sub n is less than or equal to, and therefore the series C sub n is less than or equal to series B sub n. Okay? Now here's the thing. If the smaller series diverges, then that implies that the series above it or larger also diverges. So it's really two different cases, and it boils down to this, and I'll put this down here. I'll write it in English. If you think, maybe you have some sort of idea that your series, okay, A sub n might converge, Now, how do you prove it? Then find a larger series that you know about, that series that you know converges, that you can tuck your series under, that you know a larger series converges. By the way, all the math is written out up here. I typed it up, I think. There you go, right there. Okay. So that's case number one. If you think your series converges, find a larger series that converges, and that's how you prove it. You just go, hey, this series is bigger. I'll show you how to do this. And it converges. So my series has to converge as well. The other case, these are two cases, if you think that it diverges, if you think your series, I'm thinking it actually diverges, then find a smaller series, terms are smaller, that diverges. Okay, and the way you can look at that is, oh, I found C sub n. I said C sub n. C sub n diverges. And you know what? It is less than or equal to series A sub n, so that implies this guy diverges as well. Looks like that. Of course, if you go this way, series B sub n converges, then what does that say? You got series A sub n that's less than or equal to it. It implies that this guy also converges. So you get if it converges, find a lid above. If it diverges, find someone below that pushes them to infinity. It takes a little bit of thinking on your part to ponder this. Here's a couple of examples. All right, this particular guy right here, I would not run the basic comparison test on. I wish I know of a better example, but I'm going to work with this one and show you how this works. You got to understand something first right off the bat. If you're going to use the comparison test, you have to understand the following truth. For fractions, okay, the one with the larger denominator is actually smaller, and vice versa. What am I talking about? I'm going to write two fractions, 1/4, 1/5. The 5 is bigger. 5 is bigger than 4, yet 1/4, 1 over 4 is bigger, or I'll write it the other way. 1 over 5 is smaller. So 1 over 5 is smaller than 1 over 4, right? I'd rather have 1/4 of the pizza than 1/5 because I'm hungry or whatever, okay? So here's the thing. Lot to talk about here, so I'm going to take my time here. There's a lot of information I'm throwing at you here that's going to help us. This is for intuition, but here's how you actually do it. What I do when I'm doing a problem and I figure, oh, I'm being told to do this, say, with the comparison test, is I actually look at the lead powers. A lot of times this is what it's about, is rational expressions like this one over here. And I'm saying, you know, this guy, I'm going to get rid of that. He looks like, you know, series 1 over square root of n, or series 1 over n to the 1/2 power. And you know what? This is me thinking. I happen to know that that guy is a divergent p-series. Remember those guys? So I'm going to do a comparison to a divergent p-series. In other words, 1 over square root of n minus 1 is almost identical to 1 over square root of n, you know what I mean, as a series. Now, I know that he diverges, so my thinking is my series diverges. So I'm going to take this series and go, well, I've got series n is equal to 2 to infinity, 1 over square root of n minus 1, and here's the rub. For divergence, I got to find somebody over here that diverges, okay? I got to do it legally, okay? So here's the thing. I'm going to do this. 1 over square root of n. Why am I so confident in this? I don't know why. The denominator here, which denominator is bigger? This guy's denominator is actually bigger. So that means that the ratio 1 over square root of n is less than or equal to 1 over square root of n minus 1. Bigger denominator, smaller fraction. Okay, another way you can write that to convince your friends is you might say, or you could say something like, well, I know that the square root of n is actually bigger than or equal to the square root of n minus 1, but I flip them over, square root of n is actually less than or equal to the 1 over the square root of n minus 1. Okay, now here you go. So, but I know series 1 over square root of n diverges, and you tell people it's a p-series. So, therefore, by the comparison test, okay, series 1 over square root of n minus 1 also diverges. When I think of using it for divergence, I think of the lesser or the smaller series just pushing this bigger one to infinity. So in other words, 1 over square root of n minus 1 goes to infinity. It's whoops, wrong one. 1 over square root of n without the minus 1, okay? But he's less than or equal to the series 1 over square root of n minus 1. Or should I say, this guy that we wonder about is bigger than infinity. It has no choice. He's pushed to infinity. Okay, this is a tough one. Now, people have trouble with this particular series. Try this one. This one to me is a little more straightforward. Like I said, I would have done this one a different way. But look at this one. Whenever you see a series and it's got trig in it, you know, as a term or whatever, and we've got one right there, right? Then what I like to do is tell the world, I think I might need room for this, but I'll go, I know that cosine, here's the thing, this is how you get a sine or a cosine corralled, if you will. We know that these guys are blazing between minus 1 and 1, okay? And in fact, if that term were not there, if that cosine term were not there, I'd be looking at n over n cubed, let's say, plus 3n, and I'm thinking, you know, that's like 1 over n squared. Now you know how my brain thinks about these things. I'm thinking if that weren't there, it's almost like 1 over n squared, which I'm thinking, oh, that's a p-series with p equals 2, and he's going to converge for us. So I'll continue with this argument, okay? So therefore, n cosine of n is less than or equal to n minus n over here. So n cosine n plus n is less than or equal to n plus n, and over here minus n plus n. Okay, so that's 0, isn't it? And then I'm going to divide everything by n cubed plus 3n. So divide by n cubed plus 3n, divide by n cubed plus 3n, and I've got this following problem. I've got that I'm not going to care about this because I'm thinking it's going to converge. So I'm going to look at the top now. I'm going to look at cosine of n plus n divided by n cubed plus 3n is actually less than or equal to 2n over n cubed plus 3n. If you want, you can simplify that a bit. I think I need some room for this work. I don't have any room. What do you think about that? So let's take this guy down to the top of this page. Okay. And so what I'm saying is, let me see where you went. Our series, cosine of n cosine n plus n, right? All over 3n what? N cubed plus 3n, okay. Okay, so n cubed plus 3n is less than or equal to, after a little bit of work, 2 over n squared plus 3. 2 over n squared plus 3. You know what you can do? You can keep going. You can go, you know what? That's less than or equal to 2 over n squared. Why? I got rid of the 3. So what happened? I made the denominator here, denom, is actually smaller. I decreased I decreased the denom. So, see how tough this test is? So this is actually true. 2 over n squared plus 3 is less than or equal to 2 over n squared because n squared is actually smaller than n squared plus 3. Therefore, the reciprocals, he's larger. And then you just say, you know what? This is a convergent p-series. And that implies, therefore, finally, this guy. Well, I should have said it this way. Series 2 over n squared is a convergent p-series. That implies our series, finally, n cosine of n plus n all over 3n, I did it again, n cubed plus 3n is also convergent. And in this case, what's happening is you got some sort of series, I don't know what it's going to do, but it's less than or equal to a finite convergent series. Took a little work here, okay, to get that one done, but we did it. You know, we used this game of trapping cosine between -1 and 1, build up the series, and then get a little bit clever. Yeah, the comparison test requires us to be pretty clever with it. The next stop is going to be for us to look at the limit comparison test, which I think you'll find is much more straightforward. Okay, but like I said, sometimes you cannot avoid this one. All right, thanks for listening. Hope that helps. I know. That one's a confusing one.